Good afternoon. Today we're going to be talking about section 3.9, derivatives of logarithmic and exponential functions. And this is kind of a meaty chapter or section. So if you need to watch this video more than once, there's nothing wrong with that. And if you need a few more examples or anything like that, don't be afraid to email me. So let's start by going over some properties of the natural log of x and e to the power of x. E to the natural log of x equals x for all values of x greater than 0. And the natural log of e to the x equals x for all values of x. Y equals natural log of x if and only if x equals e to the y. That is, if we take the natural log of both sides, we get the natural log of x equals e to the y, or the natural log of e to the y, natural log and e cancel out, we're left with just y. For real numbers x and b greater than 0, b to the power of x is the same as e to the natural log of b to the power of x, which is the same as e to the x times natural log of b. So that's just a cute way of restating the very last one, and we'll get there. The natural log of a plus the natural log of b is equal to the natural log of a times b. The natural log of a minus the natural log of b is equal to the natural log of a divided by b. And finally, the natural log of a to the power of a number b is equal to b natural log of a. And these should just be a refresher. You should have learned these in some sort of algebra class. If you don't recall them, that's okay. That's why we're including them here. But just so that you remember them, here they all are. You might want to write these down until you get familiar with them. So let's talk about the derivative of the natural log of x. The derivative of ln of x is equal to 1 over x for values of x greater than 0. And the derivative of the natural log of absolute value of x is 1 over x for x not equal to 0. Remember, we can't put negative numbers and we can't put 0 into the natural log of x. But if we take the absolute value, then we get rid of the problem of negative numbers, and we just have a problem with x equals 0. Now, if u is a function and it's differentiable at x, and u of x does not equal 0, then d dx of the natural log of the absolute value of u of x is equal to u prime of x over u. And this is just a relic of the chain rule, which we'll see used in the next few examples. So let's find some examples. And here I'm going to do this example two ways. So find dy dx for y equals the natural log of 4x. So let's use the chain rule, or oh my goodness. That would lead to our answer being this bad boy right here. So u of x in this case is 4x, so we put that in our denominator, and u prime of x is just equal to, is just equal to 4. So 4 divided by 4 over x is just 1 over x. Now we can do this in another way, and that's using our log rules. ln of 4x is equal to ln of 4 plus ln of x. So when we go to take the derivative of each side, we get the derivative of ln of 4, and the natural log of 4 is just a number, so we know that that term goes to 0. And we're left with taking the derivative of ln of x, and we know that that's 1 over x. So our answer is 1 over x. So either way you approach this problem, you're going to get the exact same answer. And that's kind of one of the cool things I think about mathematics. So let's move on to another example. This time I want you to find the derivative of y equals natural log of absolute value of secant x. So just like before, we're going to use the chain rule. The derivative of the outside is 1 over the inside. So we get 1 over secant x times the derivative of the inside. The derivative of secant x is equal to secant x tangent x. So the derivative of the inside looks like that. Then we get secant x cancels out with secant x, so we're left with tan of x. And that's our final answer. So now let's talk about b to the x, where b is a number greater than 0 and doesn't equal 1. Then, for all values of x, d dx of b to the x is b to the x natural log of b. And we're going to see this in kind of a convoluted example, but this is the one from the textbook. So let's just dive right in. Find the derivative of g of t equals 108 times 2 to the power of t over 12. And for this one, we're going to need to use the chain rule. But first, let's start with the constant multiple rule. So g prime of t is going to equal 108 times the derivative of 2 to the power of t over 12. And now we can take the derivative of the outside, which is 2 to the power of something, and that's going to be, we leave our constant multiple out here, 2t over 12 natural log of 2. And then we need to take the derivative of the inside. Because we're not just dealing with we're not just dealing with one singular t, we're dealing with t to the power t over 12, we need to take the derivative of this. So the derivative of t over 12 is just going to be 1 over 12. So I have 108 divided by 12 times 2t over 12 times the natural log of 2. All of that equals 9 times 2t to the 12, t over 12, times the natural log of 2. And maybe this example didn't seem super intuitive, and it's not very intuitive, so I'm not really sure why the textbook chose it. But this gives us a good example of using the chain rule and also using our newfound knowledge of the derivative of b to the x being x times, b to the x times the natural log of b. So what about log base b? Now, log base 10 is what we're used to using, and log base e is the same as natural log of e, so let's write that. Log base e of x is the same as the natural log of x. So if b is greater than 0 and b does not equal 1, then d dx of log base b of the absolute value of x is 1 over x times the natural log of b. And let's dive right into an example. And again, this example doesn't really give us a whole lot to work with. It's not very straightforward, but that's okay. So we're going to start with using the product rule for this one. So I'm going to have n times ddn of log 2 of n plus log 2 of n times dn of n. This first term becomes n. We use our new rule, and we get 1 over the inside times the natural log of the base, which is 2, plus log base 2 of n, ddn is just 1. So our final answer, once we get everything out of the way, is 1 over ln 2 plus log 2 of n. And that's our final answer. Now there's one more section we're going to cover in this video because it's really short, and this section is 3.10, derivatives of inverse trig functions. And all you need to know about an inverse trig function is that if I apply sine to some value theta, I get a value. And if I apply sine inverse to sine of theta, I get the value theta. So sine inverse undoes the work that sine does, and it lets us access this value right here. So we need to know the derivatives of these bad boys. So the derivative of sine inverse is 1 over square root 1 minus x squared. The derivative of cosine inverse is negative 1 over square root 1 minus x squared. The derivative of tangent inverse is 1 over 1 plus x squared. The derivative of cotangent inverse is negative 1 over 1 plus x squared. And then the derivative of secant inverse is 1 over absolute value of x times square root of 1 minus x squared, and the derivative of cosecant inverse is negative 1 over absolute value of x times the square root of 1 minus x squared. And these might not come in handy today, but if you are moving on to Calculus 2, these are going to come in very, very handy. So if you are moving on to Calculus 2, maybe keep these in your back pocket and be familiar with them. If you're not moving on to Calculus 2, then I recommend just memorizing them for the usefulness of this class, and then after the final exam, you can go ahead and forget them. But that's it for me today.